Hello, everyone. Welcome back. Welcome back to Calculus 1000. I hope that you all are having good time out there. It's cold a little bit, yes. Make sure that you layer up enough. I think it's that time of year. We should appreciate so far. We had good fall, yes. And those who, I said one before, but I should remind you again. Sometimes you will feel a bit more tired than usual or a bit fuzzy every day. I think one of the things you should check is if you are getting enough vitamin D, because sunshine usually is not out there. And check with your family doctor. Get some vitamin D supplies. Don't be sleepy like I am, okay? Today, we will continue working on fundamental theorem of calculus. I hope that last time I was able to show the level of appreciation you should have toward the fundamental theorem of calculus. We did part 2, which was about calculating or evaluating integral. I will quickly remind you, recall what we had. Do 1 or 2 examples. I like these examples because it kind of now tells you that whenever you get a tool, this tool could be a strong tool like fundamental theorem of calculus or other thing, you better go back, reevaluate what you have been doing, and see if that tool will bring you new things or not. These examples that I will do today are related to that. And then we will start fundamental theorem of calculus part 1, which is another interesting, fun story. Before I start, is there any questions, any comments? Let's quickly recall what was FTC part 2. Well, usually people teach FTC part 1 first, obviously, because of the numbering. But for us, I think that came more natural to start with 2, and then we go to 1. What does it say? It says that if you know an antiderivative of your function on an interval, on a given interval, then you have a strong statement about how to evaluate your definite integral a to b of f of t dt or f of x dx. This says, well, if you know an antiderivative, you're almost done. Evaluating a definite integral, if you know what is antiderivative of the integrand, is just plug in 2 values into the antiderivative and then subtract that. So this was the story. Last time we did so many examples that now, well, since we have the knowledge of antiderivative, we know FTC part 2, we can evaluate these integrals. Well, for example, very simple, nice example here, integral of secant squared x from 0 to pi over 4 dx. There was no other way for us to evaluate this integral before. Like the Riemann something would just take us so much. It cannot do all the work for us. There's absolutely no other way than doing FTC to evaluate this integral. So what we have is that, okay, pay your respect, say that I'm calling you, and then you know what is antiderivative of secant squared? Tan x, thank you. And you go from 0 to pi over 4, meaning, well, don't let things confuse you. Like, don't mix up things. This is just a notation. It has no internal meaning. We are giving it the meaning that, by that, we mean evaluate this function at upper limit minus evaluated at lower limit and subtract those. Tan of pi over 4 is 1 minus 0. That limit, that integral is 1. So we did examples like that. Now I want to go a bit more back and say that, remember back old painful days of evaluate the Riemann sum, find the limit? You don't remember that? You don't remember that? Those painful days of evaluate Riemann sums? Oh, then I wasn't very successful of showing you how painful those things are. I should think again. Now I want to use FTC to do that part. Use FTC to evaluate given limits. Let me just make sure that I'm putting the right things. 1 plus minus could change the game a little bit. Yes. Limit of n goes to infinity, I goes from 1 to n, I squared over n cubed plus 1 over n. Well, here, there's a bracket over there. Also, we can look into this guy. Okay. These are limits of Riemann sums, yes? And, well, we can do this one. We actually did a bit more complicated examples than this one. We can evaluate that and go down to the, what is the sum for general n and define limit. But I don't want to go in that direction. I'll show you on the first example what I want to do here, and then I'll give you some time to do the second example yourself. Here what I know, this is now the key point. I want to see this as for some function f and some interval ab, I want to say that this is Riemann sum of this function and that interval. Once I have that, and my function, if my function is a nice function, then I can say that this limit is supposed to be this value, integral from a to b. So the first step for me is find f, find a, find b, such that I can get rid of all these summation, limit thing, and write one integral. How is FTC going to help us? Well, if you know that FTC can be applied here and evaluate that thing, well, basically we use FTC to evaluate this whole limit. Yes? So in this case now, I want to go play that pattern finding game. Delta x f of xi is equal to delta x is always a term like b, a number over n. Yes? Here I can factor out 1 over n, and I can write I squared n squared plus 1. I'm looking for function and ab such that this thing is going to be that part. Well, right away, I say, I'll take this one as delta x. Well, that implies that b minus a over n must be 1 over n. And from there, I can conclude that, well, b minus a must be 1. And we have a freedom there. We can choose a to be any number. But in this specific case, as I did in most of the cases, we can set a equal to 0, so b is equal to 1. OK? So now we know that this is 0, this is 1. Another thing that I know by fixing delta x to be 1 over n is that, OK, now I know xi is going to be a plus I delta x, which says, based on my choices, a equal to 0, I, delta x is 1 over n. So delta x, sorry, xi is going to be I over n. OK? Xi is 1 over n, and my hope is that this guy is going to be xi, f of xi. Xi is I over n, so I have I over n squared, so this is xi squared plus 1. There we go. Everything worked out nicely. Not only I found a and b, I also figured out that f of xi must be xi squared. In other words, I have everything now there. I can go ahead and try to compute my limit, Riemann sum, and everything there. Is there any questions so far before I do the other part? OK. Let me rewrite that last piece over here with the given thing. So I know that this limit is going to be integral from 0 to 1, x squared plus 1 dx. I wrote that limit of Riemann sum as a definite integral for a known function, known a, known b. Now I can use, this is the part FTC comes in. FTC does evaluate the definite integrals without going through the painful Riemann sum thing. It says that if you know what is the antiderivative of this, which I know, then you just need to do this. And by that, we mean, oh my God, so many lines I'm drawing today here on board. By that, I mean you plug in 1 there. That will give me 1 over 3 plus 1. Plug in 0. Everything is 0. So then I get 4 over 3. Look at this board. Learn 2 things. 1, how to solve questions like that. 2, never write it like that. This is awful writing on board, yes? Write better. Someone said yes. It's awful writing. See? Any questions? Any comments? Are we all good? Do you want to work on the other one? Do you want to do anything? Yes? Do you want to work on the other one yourself? I know, not yourself. So I'm going to ask you, not work on this alone. Work on it with a friend. You try to work each other to figure out. The key point is to write this as integral of a function from a to b. Go ahead, you have 1 minute. You're not working alone, you're working with a friend to figure out what is F, what is A, what is B. Go ahead, I want to hear some chat. Maybe another 10 seconds to wrap up things. I want to write that summation as delta x times f of xi. Well, I can rewrite this inside this thing as that. And the term here has all the good things in it to be delta x. Yes? Delta x is always a number over n. So delta x I can take, well, let's see if it works or not, but I can take it like that. And that will imply that b minus a is going to be pi. Okay. Before I go and set a equal to 0, I said most of the time, like all of the time, a equal to 0 is easy choice, works. But I want this time, I want to use a bit different thing for finding A and B. And the pattern I want you to see here is that this is cosine of something here. And that thing is written as a number plus I times delta x. Yes? What does that give me when I'm trying to do Riemann sum? A plus I delta x gives me xi. So this whole thing is cosine of xi if I take a to be pi over 2. And I can move from there on because now I have a is pi over 2. I know that b minus a is equal to pi. So that will imply b must be pi plus pi over 2, 3 pi over 2. I also figured out something else already. I know that xi, with all those things that I have fixed, f of xi is nothing but cosine of xi. Aren't those everything that we were looking for? This already I found what is A, found what is B, and I found what is the function. F of x is equal to cosine of x. I'll give you 10 seconds to turn those question marks to a verbal question for me. Any questions, any comments so far? Yes, please.
You Times I delta x or A.
Oh, see, it's not the matter of finding. I'm trying to match my patterns there, yes? I'm not saying definitely, but I'm saying that, look, xi is always, for general AB, is defined as A plus I delta x. This is general formula, yes? And I see that pattern there. Because my delta x, I already fixed to be pi over n, yes? And, well, in that case, if I set A to be pi over 2, everything matches there. It's just like, I'm not saying anything with 100% sure point. I'm just trying to see, oh, if I pick A to be pi over 2, do I have xi here? Yes, happens to be right, yes? I am trying just to figure out the pattern, and then everything worked out well. Did that answer your question? Yeah. Thank you. Any other questions, any other comments? Yes, please. We can have A could be chosen, or B, only one of them, could be chosen to be any number you like, yes? There is only one tricky thing here. For example, if I take A to be 0, then A is 0, I delta x is xi. In that case, you're dealing with cosine of pi over 2 plus xi. So your function will also change a little bit. See, if A is 0, I delta x, which is I pi over n, is xi. And you have this extra term pi over 2 there, which you have to take it in, yes? It's not A, it's not part of delta x, so it has to be constant from the function itself. Yes, you can choose A to be whatever you want, but accordingly, the function may change as well. Any other questions, any other comments? Okay. Now that I have written this limit in that form, I can go ahead and say that FTC part 2 gives me the tool to evaluate it. What is antiderivative of cosine x? Louder, what is antiderivative of cosine x? Sine x. And if FTC says you just evaluate it 2 times, and it will give you what you want, because now I can evaluate this limit, but this integral, and that integral was nothing but the limit that I already had. This is negative 1 minus 1. See, no matter how hard you work, finding general formula for this summation for general n, it won't be easy. I wanted to say it's not possible, but yeah, well, in some sense you can make sense of that. If you know, for example, what is, I'm not actually sure. I was trying to say what's Fourier series, but yeah, that would also take a little bit of work there. Well, I can say that's a very difficult task to evaluate this sum and, well, afterward finding limit. But now, being able to write that sum as limit of Riemann sum, we can turn it to definite integral, and we have a very strong tool to evaluate the definite integrals, which is fundamental theorem of calculus part 2, and then we evaluate. Any questions, any comments? Or me?
I actually
FTC part 2. FTC part 2 is done. We don't have much to say about FTC part 2. It's just like, it's a tool, was a huge story. It's a tool that tells you how to evaluate your your definite integrals. FTC1 is a bit different story. This is about finding derivative of some specific functions. Let f be a continuous function on the interval AB. Well, I can start saying well, it's continuous everywhere, but I can limit it there. Now, if f is positive, just to make things a bit nicer, I will assume f is positive. But this game, you can play it with the negative functions as well, or positive negative functions as well. So I can start finding area of the region under the graph of this function from A. Well, I usually go from A to B. I don't want to do that. I want to go all the way to some number. Let's call it x. And I want to define my function that way. Let's say gx, the function, assuming that f is positive, it's continuous, is the area of the region under the graph of f from A to x. What does x mean? Well, x is a variable. You change it, you will get different region, you will get different area. You get smaller, you get different thing, you get different thing. Different region, different area. And that shows that the region, the number I'm working with depends on A. It says how far you go from A, or how far you go from 0, to fix this region's interval. Yes? Obviously, it's a function of x, but since we know if f is positive, this is going to be given by A to x of. So I will go from A to x. Here, there's a very small point. It's easy. You need to do not write anything. Just figure out this thing for once, and we will throw it out. Don't write anything. Just pay attention here. Remember that I said when you're integrating, the integrating variable is a dummy variable. You can choose to be anything you like. So I can go and say f of box, d of box. Yes? Here, since I already used x as the bound, this x should not appear as the integral variable. So when I'm defining my function this way, it's obvious, it should be obvious to you that I should use a variable here, which is not x, because I already used x there. What I wrote there is in general true. It doesn't matter what function is positive or not positive. I'm talking about integral of f of t dt from a to x. This is a way to define a new function. I'm integrating my given function from a to a variable x. For example, if simple example here would be if f of t is t, for example, very simple, then g of x is from, say, from any point, I'll go from 0 to x of t dt. And in that case, I can evaluate this integral, and I say that, oh, here, that's what I meant. x squared over, because antiderivative is t squared over 2. You evaluate at x, you get x squared over 2. Evaluate at 0, you get 0. So the function x squared over 2 can be presented as a function integral given by that. Any questions, any comments so far? Because now I have to move and tell you what is fundamental theorem of calculus part 1. Yes, please, sorry.
Optimization problems.
I see all these. See, this is now a function. Yes? And you can now ask any questions that we had for calculus about this function. Yes? For example, does it have limit? Because it's a function of x, yes? Can you, when x goes, for example, to 0, what will happen there? Or is it continuous function? Yes? Can I use it to maximize something? Sure. Oh, before that, what is is it differentiable? Can I differentiate this function or not? So we are fixing type of function, which is, by the way, it's a good general function. It's general enough. Type of function, we want to see if I know my function has been defined this way. Can I say something about it? Again, singular level of regularity is something. Is it continuous? It is differentiable. And fundamental theorem of calculus says, yes, it has limit. It is continuous. Even more, it has derivative. It's differentiable. And fundamental theorem of calculus, part 1, tells you what is the derivative. So that is what we have now here. FTC1 says, okay, I'm writing these conditions again so that let f be a continuous function. This could go from A to B. I will write just general. Then gx defined this way is differentiable at all the points. And even more, I can tell you, or FTC can tell you, what is the derivative of such function. The derivative, or in other words, d dx of a to x of ft dt. You want me to put bracket like that so that you know that this whole thing is giving me a function, and I want to differentiate that. That derivative is the integrand. Did you pay attention there? It's so simple, you cannot believe it in your eyes. Like, what? And yes, fundamental theorem of calculus part 1, even if it is for nothing else, the simplicity of this result should tell you that, oh, I am important thing. Because so complicated things can happen, so many complicated things can happen here, but finding derivative is just take the integrand. Wait, what did I do? I took the integrand, I plugged in x into that. Why did I plug in x there? Why didn't I put ft? Yeah? T has no meaning there. The function we are working with is a function of x. So its derivative should be also a function of x. the t doesn't make, made sense. We could make sense of t if we had the whole integral. It was part of the integral. Outside the integral, t has no meaning. But x has a meaning. This is the input of that thing. And the derivative will be equal to that. Does that make sense? Yes or no? Yes, please. Sorry, what was that example?
T squared over 2?
No, after okay. See, I jumped 2 steps. Maybe you're thinking of this. See, t by itself doesn't have any meaning there because you integrate, t will go away. That was part of the game of integral. Now I plug in, I get x squared over 2 minus 0, which is x squared over 2. Again, there's no t there. Yeah? Any other questions? Yes, please.
Are we supposed to assume that a equals 0?
A could be any constant number. Any constant, 1, 2, 0, million. And it's a good thing to see. If I pick this to be a different number, a is, instead of a is another b, another number, then that function that we defined is this function plus a constant. And that constant will go away when you differentiate. That's why it really doesn't matter what is. The function itself depends on a, but the derivative doesn't depend on a. Any other questions? Any other comments? Let's do some examples. Simple one, complicated ones, funny ones, cute ones, everything. We have a whole bunch of examples. What is derivative of 0 to x of sine t squared dt? What about 2 to y of x cubed minus 3x squared plus 2 dx? Oh, sorry, this should be dy. How about okay, the first one, okay, maybe before I go through this, I want you to just pay attention again to the formula I have written here. Always remember, we are dealing with 2 different variables. One is the integration variable. That will go away. Doesn't matter what it is, at the end it will go away. The other one is the variable that defines the function, the input of the function. I am differentiating with respect to that x, that variable. Now, the names are not important. I'm differentiating with respect to the variable which is up there. Inside here, I don't care what are there because that's dummy variable. Someone can change it to anything they want. Here, this is the derivative says that you just take the integrand and make it or plug in the right variable into that. How about this one? Okay, it goes from 2 to y. I'm differentiating with respect to y, so everything is good there. The integration variable is x. That's cool. I'll just take the integrand and plug the y into the integrating variable. Doesn't matter what is a. The only thing looking at is that this is a constant, this is the variable. I'm differentiating with respect to the same variable. The integration variable in this case is x. Okay, so that will go away, and I'll take the integrand, and I plug in what I was differentiating with respect to. Any questions, any comments? Yes?
Why do you not care the negative?
What is the lower value? Yes? Okay, I'll do this simple calculation. Okay, let me do one example, and then I'll come back to that, okay? Any other questions, any other comments? Okay, how about I give you this one. We are all good with F. Oh, by the way, sorry. I didn't pay enough respect there to the tool I was using. I should always cite the tools that I'm using. FTC1 tells me what's happening there. Okay, how about I'll give you 45 seconds. I want you to work on your own examples. After 45 seconds, you will have a chance to talk to the friend sitting next to you. 45 seconds, you're trying to answer those two questions. Go ahead, please. 45 seconds starts now. And you're not talking to anyone. You're trying to do it yourself. Pardon? Done. No, yeah. This doesn't say differentiated. It just take the integrand, plug it in x. That's it. 45 seconds, you're trying to do those two examples yourself. Okay, your 45 seconds is done. Now, I'm hoping that someone who's sitting next to you, you trust them, you can share with your mistakes with them. Now try to swap the work you have done or show them what you have done and try to see where they made a mistake. Go ahead, you have another 45 seconds. You're working on the solution of your friend, not your own. And trying to convince them, oh, you made a mistake. No, this is good, or no. Making mistakes is a good thing if it happens at the right time. Can anyone tell me what is the result, the derivative of the first one, the first derivative? Yes.
To the negative 100.
E to the power negative 100. How many of you found that same thing, the correct derivative? Go ahead, show. Don't worry. Come on. No one is going to grade you. What else you found? What else you found? Can I hear? Other than e to the power negative 100. Did you find anything else? Yes, please. 0. Interesting. How many of you found 0? Okay, bunch. Can anyone else tell us something different? Oh, you guys are so afraid of making mistakes that you will keep the mistakes for the bad timing. Yes?
Negative 100 minus e to the negative 1.
That's another. E to the power negative 100 minus e to the power, no, minus 1, you mean. You plug in. OK. Definite integral. I don't know what is the value of that, but it is a constant. If you have both limits numbers, this will be a number there, and you're trying to differentiate a constant. Derivative of constant is 0. Wait, didn't you say that you just take the upper one, plug it? No, I said that if the upper one is the variable that I am differentiating with respect to. Here, the upper one is not variable. This is a constant number, and then done. How about the second one? How about the second one? Do I have any answer for that?
Flip the integral and then make it negative and then.
I want to turn that function, that integral, into this form. It is not in this form. FTC cannot be applied here. Instead of that, we will use the properties of integral, which says that you can swap the limits, but you will get a negative coefficient. And negative works nicely with the derivative. And fundamental theorem of calculus, part 1 now can be applied, and it will give me this. OK? Yes, the original one, I could not apply that, but now I can, after flipping, I can apply it. Now, back to your question. What if I want to differentiate, but instead of A, it is B here? I want to show that you can always go back to A. Well, let me rewrite this integral. I can go from B, if I can go from B to A, and then I go from A to X, I get the same function, yes? I can always split my integral on the given intervals, yes? Now, look at this guy. What is that? Well, it's a number. It's a constant, yes? And as you showed, when you differentiate constant, this part will be 0. And now we end up with getting derivative of this thing. Back to the original one. So it doesn't matter what is the lower limit. The only thing I care there is that the lower one must be a constant. Yeah? Yes, please. No, I am saying that this thing is not 0 itself. It's a constant. It will give me some number. 0.2 something. Yes, whatever the number is. But there is no variable here, no x that changes that number. It's a constant always. Derivative of constant is? The reason here is that the both limits are constant. There's no variable playing it. T is integrating variable. It is very internal to the integral. It has no meaning outside of integral. It's not changing the value of integral. It's used to evaluate the integral. Have a great day. You come back tomorrow. We will play a little bit more with the fundamental theorem of calculus part 2, and then we will go ahead and try to do more work. Have a great day. See you all tomorrow.
5